Lesson 2, Inverse Functions and Relations. Here we have an example where we show that inverse is simply undoing or going backwards. This is not math, this is just so you've got the general concept. We have apples going into a box that turns them into lemons. The lemons then go into the inverse of the box and come out as apples. Notice that this would be the same thing as if we took these lemons and we turned around and we went backwards through the box. Okay? The output of the function is the input for the inverse, which the output of the inverse is the input of the original function. I know, it's very circular. By the end of this lesson, you will be able to find the inverses of a function mathematically. You'll be able to determine if two functions are inverses of one another using compositions, which was our last lesson, and you'll be able to solve problems involving inverse functions. The language objective is that you will be able to describe the process employed to find the inverse function. Now, what happens when we combine a function with its inverse function? We have gone from a lemon to lemonade, back to a lemon. Okay, remember, a function does, the inverse undoes. Now, do, undo, function, inverse function. A function takes a starting value, performs some operations, and creates an output or answer. The inverse function takes the output answer as its input, performs operations, and arrives back at the starting value. So in other words, we have sine theta. That's the sine of an angle is equal to the ratio of the sides. Now, if we do the inverse sine, this is not a reciprocal when you put a negative exponent, for lack of a better term, the negative one. When you put a negative superscript on a function, it's not the reciprocal, it is the inverse. So if I do the inverse sine of the ratio of sides, which, notice, was the output from the other, I'm going to get the angle back. So the two values here are the angle and the ratio of sides. If we swap them around, we're just doing the inverse. This process can be stated as a composition of functions. Functions f and g are inverses if and only if. That is not a misspelling. IFF is if and only if. F of g of x is equal to g of f of x equals x. A function composed with its inverse function yields the original starting value. Think of them as doing and undoing one another, leaving you exactly where you started with x. Okay? Now, that's all well and good, mumbo jumbo. How do we actually find the inverse of a function when we're given a function? Well, it's actually quite simple. If a function is in function notation, simply rewrite it in y notation. Okay? Simply rewrite it in y notation. Then swap the x and the y variables, make all the x's y's, all the y's x's, and solve for the new y. You can then rewrite it in inverse function notation. So here's an example. F of x is equal to 2x plus 7. First, rewrite it in y notation. That means I'm going to take the f of x and I'm going to change it to y. Okay? 2x plus 7. Now, I'm going to swap the x and the y. So the x goes where the y was and the y goes where the x was. At this point, I'm going to solve for y. So I'll subtract 7 from both sides, divide both sides by 2. This is the inverse of the function. Now, I could write this as f to the negative 1 of x is equal to 1 half x minus 7 halves. That's putting it back in function notation. Now, something to be noted is that this newly formed inverse will be a relation, but it may not necessarily be a function. You need to check to see if the inverse is a function or not. Remember that a function is defined as for any given input, there is one and only one output. It also passes the vertical line test. Now, in this case, the inverse relation is a function, but it's not always true. So consider this subtle difference. Inverse of a function, the relation formed when the independent variable is exchanged with the dependent variable in a given relation. This inverse may not be a function, might not be a function. It could be. Inverse function. If the inverse of a function is itself a function, it is then called an inverse function. So we have the inverse of a function and an inverse function. Remember, the inverse of a function may not always be a function. The original function must be a one-to-one function to guarantee that its inverse will also be a function. One-to-one. If for any given input there's one and only one output, and for each output there's only one and only one input, then you've got one-to-one. Now, a function is one-to-one if and only if each second element corresponds to one and only one first element. Basically, each x and y value is used only once. Use the horizontal line test to determine if a function is a one-to-one function. So remember, if it's a function, it has passed the vertical line test. If it is a function, it has already passed the vertical line test. So what we're going to do is we're going to apply the horizontal line test, going across. And if it passes the horizontal line test, meaning a horizontal line only crosses this function once, then it is a one-to-one function, and its inverse will also be a function. The inverse of a function is a set of ordered pairs obtained by interchanging the first and second elements of each pair in the original function. Basically, swap x and y. So for function f of x, the inverse of the function is denoted by f raised to the -1 of x. The original function is a one-to-one function. The inverse will be a function. One thing to note, this means inverse, okay? Inverse, not reciprocal. Now, if a function is composed with its inverse function, the result is the starting value. Think of it as the function and the inverse undoing one another when composed. Now, what we're going to look at is, consider the simple function f of x is equal to 1, 2, 3, 4, 5, 6. Its inverse, we swap the x's and the y's, so we get 2, 1, 4, 3, 6, 5. So we want to prove to ourselves, algebraically, using compositions, that they are inverses. So f of f to the -1 of x. F of f to the -1 of 2. Well, remember that f of the -1 of 2. So it means 2 is going to be my input. So my 2 is input. What is the output? Is 1. So this right here is equal to 1. What is f of 1? I come back up here. F of 1 is 2. And 2 was my original input. So notice you get back what you started with. Okay? You can do the same thing with the other 2 points. Okay? Input 4 to get f of f, to get the inverse, you get 3. Input 3 to f of x, and you get 4. Input 6 to the inverse of f, and you get 5. Input 5 to f of x, and you get 6. So right here, okay, I input 4, I get out 3. I input 3, I get out 4. I input 6, I get out 5. I input 5, I get out 6. If you need to, pause and study this for a moment. Now, here are some examples that you're going to try. Pause the video, decide your answer, and then check. Given function f, find the inverse relation. Is the relation also a function? Remember, when you're given a set of ordered pairs, it doesn't get much easier than this. You simply swap the x and the y values. So go ahead. Function f is a one-to-one function since x and y values are used only once. Since function f is one-to-one function, the inverse relation is also a function. When I do the inverse, I get 4, 3, -2, 1, -1, 5, and 2, 0. That's it. For this second one, determine if the inverse of this function is the invert. Determine the inverse first, And then is it also a function? Well, the one thing I can do is I can look immediately at the y's and go 2, 0, 3, -1, 1, -2, 5, 1. Ooh, 1 and 1. Nope, the inverse will not be a function. But when I find the inverse, I simply swap everything. Okay? Easy peasy. Now, to solve algebraically. Solving for the inverse relation algebraically is a three-step process. Set the function equal to y. You could leave it as f of x, but that gets very confusing. Swap the x and the y variables and solve for y. Now this could be a's and b's, p's and q's, s's and t's, whatever you want, but we're going to keep it simple in x's and y's. So if I want to find the inverse of f of x equals x minus 4, okay, I'm going to change it to y. Then I'm going to swap the variables. Then I'm going to solve for the new y. And then finally I can put it in function notation. Pretty easy. Okay, take a moment if you want and pause the video. I have what you need to do here. Try finding the inverse of this. Go ahead, pause the video and try it. Okay, now first, remember we had to set it equal to y, and then we swap the variables. You should be able to do these first two things, boom, instantly. If you can do these first two things, you've essentially earned at least 1 out of 4 points if we're grading it on, say, a 4-point rubric. Okay, you've shown that, hey, I was there, I know, I got to swap the x's and the y's. That's 25%. Now, you need to solve for the new y. So now you've got to show that part of it. Well, first, I don't like the fraction, so I'll multiply both sides by y. Now I'm going to get the y's on the same side. Now, here's one of your favorite things. You're going to factor. The greatest common factor. You can take a y out. Now you have y times this expression, so simply divide both sides by the expression. Not bad. And again, just to help you out with how I would be grading this if I'm doing the rubric, the 4-point rubric, rewriting the problem doesn't get you anything. But if you get to here, that gets you 1 point. Then if you start doing some of this stuff, but you don't really have all of it, okay, you're going to get another point. Now, if you get all the way down here, okay, you'll get your 4th point. In here, you've got a couple of points. This all depends on whether you make a major or minor mistake. Major mistake, you only +1. Minor mistake, you get the +2. Okay? Just sometimes it can help to understand that you don't have to get everything. And once you get on a roll, you're going to get your answer. Graphing. The graph of an inverse relation is the reflection of the original graph over the identity line. Y equals x. That's this green line right here is y equals x. It's called the identity line. It may be necessary to restrict the domain on certain functions to guarantee that the inverse relation is also a function. We're going to talk more about that when we graph inverses. Right now, consider the straight line y equals 2x plus 3. That's here in blue. If I reflect it over this line, that means I just swap x's and y's. So 0, 3 will become 3, 0. -2, -1 becomes -1, -2. Okay, so they just swap. The new graph, which is the red dashed line, is also a straight line and passes the vertical line test for functions. The inverse relation of y equals 2x plus 3 is also a function. Now, all graphs produce an inverse relation, which is also a function. This one does. But again, the way you can tell is it's a reflection over the y equals x line, not over the x-axis, not over the y-axis, but over the identity line. Now, try some of these problems. Use what you know about inverses to answer each question. As I come to a question, pause the video, answer it, and then resume. So pause, Is 2573 the inverse of 5237? Absolutely. The x and y values from the original swap places to us, from the original swap places to form the inverse. Okay? So x and y just simply swapped. What about this one? Is the inverse also a function? Not just find the inverse, but is the inverse also a function? Yes. The inverse is also a function because 8, -4, -2, 4. There are no repeating y values. Okay? Everything is a one-to-one. Or if you found the inverse function, you would have 8, 6, -4, 2, -2, 10, and 4, 4. Pardon the fact that I did not put all the parentheses in, but I don't think you want to sit there and have me try to graph or draw with the mouse. 8, -4, -2, 4, no repeats. Okay, true or false? The inverse of the graph shown below will be a function. Well, -2 or 0, -2 becomes -2, 0. So I'm going to put a point there. Then 0, -1, or -1, 0 becomes 0, -1, sorry, I'm saying. And then 1, 0 becomes 0, 1. And I wind up with a curve going, oops, like this. So, is this a function? I think not. Okay, notice, oops, if I can do this. If I draw a straight line, it's a terrible straight line, but I cross it twice. So notice my answer is no, the inverse will not be a function. The graph fails the horizontal line test, and the inverse fails the vertical line test. Again, I drew the inverse. If you want to just do this, boom, fails the horizontal line test. True or false? Since f of x is a reflection of g of x is also the inverse of f of x. True or false? False. While it is a reflection, it's a reflection over the x-axis. It is not a reflection over, oops, it is not a reflection over this guy. Okay, remember this is the identity line. The blue and the red are not reflections over the identity line. So g of x is not, it is not the inverse of f of x. Okay, true or false? The straight line graphs shown below are inverses of one another. Are they or are they not inverses of one another? If you said yes, they are, you're correct. And again, you would have to imagine this guy like this. And in fact, the blue and the red are reflections of each other over the identity line. Now, find f of f to the -1 of 5, or f of the inverse of f of 5. Is it 0? Is it 5? Or can you not determine it because you don't know what f is? If you said it's 5, a function composed with its inverse returns the starting value. You are correct. True or false? The graphs of sine of x and cosine of x are inverses of one another. Now, before you go, whoa, I haven't learned how to graph sine. I haven't learned how to graph cosine. Doesn't matter. Right there, of the graphs of sine and cosine. So it doesn't matter what they're called. If I took away their names and said, is blue squiggly the inverse of red squiggly? You know how to do this. And your answer? False. The graphs are not reflections of one another over the identity line y equals x. Remember, that's all you're looking for. Is it a reflection over the identity line? Here's another one, similar issue. The natural logarithmic function is the inverse function of the exponential function. Since the point 0, 1 lies on the exponential function, we know that the point blank lies on the logarithmic function. Again, I don't have to know logarithms. I don't have to know exponentials. I just have to know that if you tell me for sure that they're inverses, then all I have to do is swap x and y. It states they're inverses. Given a point that lies on the graph, swap the x and y values, and you know which point lies on the inverse graph. So here, swap the x and y values to find a point on the other graph. 0, 1 lies in the exponential function graph, so 1, 0 lies on the logarithmic function graph. 0, 1, 1, 0. Boom, boom. Now, find the inverse for the function y equals 4x plus 12. Pause the video, work it out, and then start the video again. How did you do? Now, oftentimes I am going to want you to write this in function notation. So you would simply put f to the negative 1 of x is equal to 1/4 x minus 3. You're just putting in the function notation. Find the inverse for this function. Ooh, might be a little trickier, but try it. Okay, now remember, before you get too crazy, just swap x and y. Just swap x and y, then solve. When you swap x and y, I've got this whole thing cubed. Don't multiply that out. That will take you A, a long time, B, it's unnecessary. Take the cube root of both sides, and then simply subtract the 2. This one is exactly like one from our examples earlier. Find the inverse for the function y equals x plus 3 over x, where x is not 0. I put x is not 0 because if x is 0, then this is undefined. So I have to state my restriction. Pause the video now and try it. Were you successful? Did you swap x and y? Did you multiply both sides by y to get rid of the fraction? And then did you factor out the greatest common factor, which is y, and divide by the expression x minus 1? If you did, then you successfully found the answer. Boom. Y equals 3 divided by the quantity x minus 1. Now, using composition of functions, show that f of x equals 2x minus 3 and g of x is equal to 1/2 x plus 1 and 1/2 are inverse functions. Key here, okay? Using composition of functions. Using composition of functions, you will have something like this on your summative. So go ahead and find f of g of x and g of f of x. All right, are you back? Did you do the composition of each with the other? If you did, you would find that f of g of x is equal to x, and g of f of x is equal to x. On a test or a quiz, any kind of an assessment, if you are asked to prove, using composition of functions, that two functions are in fact inverses, this is the work that I would need to see. F of g of x and then g of f of x. This is the algebraic work that would prove, and then you need to have your concluding sentence. Three dots mean therefore. Since f of g of x is equal to g of f of x equals x, f and g are inverses. Now, if you did f of g of x and it was anything other than x, you could stop there. You would not have to do the second part. And then you could put, therefore, since f of g of x does not equal x, f and g are not inverses. So when they're not inverses, you actually get to stop sooner. If they are inverses, once you show one direction, you have to show the other. In summary, the inverse of a function undoes the function. Do, undo. Open door, closed door. Those are inverses. Add, subtract. Inverses. Multiply, divide. Inverses. Square, square root. Inverses. To find the inverse of a relation represented by a set of points, simply swap the x and y values. To algebraically find the inverse of a function or an equation, write it in y notation. Swap the x and y variables and solve the new equation for y. To graphically find the inverse of a function, reflect the graph over the identity line, which is y equals x. Remember that the inverse of a function is not always a function too. In order for the inverse of a function to be a function, the original must be a one-to-one function. A lot of function words being thrown around. Finally, two functions, f and g, are inverses of each other if and only if f of g of x is equal to g of f of x equals x. The composition of the two functions yield the original input. When you are asked that question, compose the two functions, one into the other into the one. If they're both equal to x, boom, they're inverses. If not, they are not. And that's it.